So please have a seat. Welcome to our session on SAR Geodesy and atmospheric corrections. We are chairing the session. Michael Eineder from DLR, Ricardo Lanari from IREA. Let's start with the first talk. The first talk is given by my colleague Victor Navarro-Sanchez from DLR. And I don't have the title to read it, so just get started, Victor.
So good afternoon, everyone. It's working okay. So yeah, my name is Victor Navarro. I'm a researcher at the German Aerospace Agency. I'm going to talk about extended time set timing annotation data set and how it can be used for InSAR applications. First of all, I would like to acknowledge my colleagues from German Aerospace Agency and also from ISA, which also funded this activity, as well as all the groups participating in the ETAT pilot study. So this is the order of my presentation. I will first start introducing a bit this ETAT product, and then I will move on to explaining how it can be used to deliver some InSAR corrections with a special focus in tropospheric phase corrections. And finally, I will show some preliminary results on the Western Alps in Central Europe, both single interferograms and also some stack processing. So what's this? The ETAT product, well, ETAT stands for Extended Timing Annotation Data Set for Sentinel-1 data. This is a new auxiliary product developed by ISA with DLR as contractor, and its main goal is to improve the accuracy of the geometric accuracy of Sentinel-1 products from meters to a few centimeters. And to achieve that, it provides some analysis-ready layers dealing with several effects like atmospheric delay corrections, ionospheric path delays, solid earth tides, and some Sentinel-1 specific corrections related to approximations during data processing. So these are delivered as some, as I said, some analysis-ready layers, evenly spaced in azimuth and range, with a 200 meters approximately resolution in the ground, and the production of this, the routine production of these products has started already, but it will be probably disseminated by the end of this year. But this is not where ETAT finished, because we already started to work in the scientific evolution of this ETAT product, including new correction layers like ocean tidal loading, pole tides, ionospheric azimuth shifts, and probably what's more important for this presentation is the tropospheric delay to height gradient. This I will talk a bit more on that. So these layers will be validated and probably included in the next iteration of the ETAT product. So, sorry. Okay. So, yeah. As I already said before, the main goal of this ETAT product is to improve geolocation accuracy of single SLC products, but the path delays corrections, the range delay corrections provided in the ETAT product are actually closely related to phase shifts, so they can be translated using the Sentinel-1 wavelength, and then we can get some interferometric correction screen by taking the difference phase from a reference, a secondary and a reference product. Of course, that implies that these products have to be co-registered to the same reference grid. And at this point, it's worth noting that the ETAT product is actually generated on a data type by data type basis. So that means the correction grid are produced following the timing and the geometry characteristics of SLC. So they are not perfectly aligned, independent from one product to another. That means the corrections, as you see in this magenta dots and these crosses, these are the geographic locations of the grid on two consecutive products, so they can be sampling different heights, especially in areas subject to layover when it's converted to radar coordinates. So a netted pilot study was run where some of these products were delivered to several study groups, and they use it for various applications like co-registration, geolocation, and also, of course, including InSAR. And the overall feedback was good, but some groups show that when applying this correction directly to InSAR, they show some visible artifacts in the correction phase screens. Like for instance, Iria and Trial Tamira noticed that. And it soon became evident that these artifacts were related mainly to tropospheric corrections, because the tropospheric corrections are closely are very correlated with topography. So the fact that we are sampling them at sometimes significantly different heights and providing the correction at this height, if you don't take into account this difference when you are interpolating to the reference grid, then you get this sort of artifacts. So resampling an ETAT product to a different reference grid has to take into account this, and we propose to do so by using this tropospheric delay to height relation to adjust the tropospheric path delay at the grid point height to the grid of the target point before performing the lateral interpolation. This is better observed with a small proof of concept. Here we took two bursts from two consecutive ETAT products, and we co-register one on top of the other using the geographic information, the lat long information. And then if we just take the differential path delay directly by subtracting both, you see some artifacts appear. I don't know if this works. You see some sort of noise-like effects that are closely correlated to the height. If you repeat this operation with a height layer, you see these artifacts are pretty much the same. So we propose to correct that, to accounting for this using this gradient, but with this gradient layer is not a part of the ETAT product just yet. So, but we can still try to estimate it from already available data, while using some local linear fitting on the using the tropospheric differential in range. Sorry, yeah. So yeah, on top. Sorry. Yeah, this is difficult. Yeah, on top you have the differential tropospheric layer, or the delay layer. That means the difference between one pixel in range to the other. And at the bottom you have the differential height. So you can do a linear fitting on both of them We do that following a sliding window linear regression with a 5 kilometer window, which is we consider that size suitable for this application, and then we get an estimated gradient, and then this gradient, just in combination with the differential height between the correction points and the actual target point, then we can get an artifact-free layer. In this case, with a frame around, because we don't consider the points where the sliding window could not be fit. Anyway, to avoid the user the burden of having to compute this in the next iteration of ETAT, we plan to include this layer as a new layer. This is, for instance, one computed for a whole data take over Alaska, where you see the typical values ranging from minus 0.5 millimeters to minus 0.2 meter. And this is at no cost to spatial resolution, because the delay is then computed for a number of support points along the integrated line of sight path. So just to show you how this correction looks, okay. So in the left-hand side, you have the uncorrected interferogram, where you see a lot of fringes, especially in the right, in the bottom right, related to this stratified troposphere, where they are correlated to topography. In the middle is the correction layer that we produce. In the right side, you see a much smoother interferogram after removing this layer, but this possibly you cannot see that at that resolution. So if you zoom out a bit, you can maybe see it clearer here, where you see that a lot of fringes from the uncorrected phase have been removed in the corrected phase. Now, in order to actually quantify this, this gain, we run a stack analysis. So we take 3 years worth of Sentinel-1 and Sentinel-B acquisition and perform a joint persistent scatter and distributed scatter interferometry analysis. So first of all, let me show you some variograms here, just to characterize the improvement that these corrections had. So these variants are obtained on the unwrapped faces of the measurement points, and they represent the interferometric. So these are obtained for pairs of points at different distances. For those we have like a double difference. We have the interferometric difference and the difference between point for short temporal baseline interferograms. So when they are shorter, these mid and long scale effects are not impacting so much the quality, but as long as we increase in distance, then all the trends or the mid and long scale effects that have not been perfectly removed, they show up as an increase of variance. So each of these soft lines represents a short baseline interferogram, while the solid red line is the average variogram. So on the left we have with the ETAT corrections, and then the right side we have without ETAT. So you see at starting 30 kilometers distance, the variogram with ETAT starts to flatten out, while the one without any corrections continues to grow. So we have a gain in variance reduction of about 6 times or 5-6 times more better for longer distances. And how does this translate to actual results? So yeah, well, this is the results, for instance, for the linear deformation component without ETAT corrections. You see a anomalous ramp going actually in the direction of the topography increase also, but it also includes also solitary tides and ionospheric effects. So all of this combined produces this anomalous ramp in the in the linear deformation, which is then removed after if we consider, if we correct firsthand all the interference with this tropospheric with this screen, phase correction screens. And the same thing happens with the topography update component, or also called the DEM error component. You also have this anomalous trend removed. So to wrap it up, so this ETAT product, the base ETAT product, will be available probably from autumn this year, or maybe winter. You can find some docs and a Python API to use this product in this website. And the new generation of this product is also already under development. We have obtained some preliminary results for that. And overall, we have observed that using this product to correct the interference produces a significant reduction on these artifacts and fringes, especially in strongly in areas with a strong topography. We also carried out a PS and DS analysis on 3-year stack, and the barrier can show a significant reduction on the overall variance that translates into some trends removed from the linear and topographic components. And the next step will be to validate and integrate the rest of the layers, like ocean tidal loading and pole tides, as well as the new improvements to the ETAT products. That will conclude my presentation. So thank you very much. I don't know if we have time for questions.
Thank you very much, Victor. We have time for 1 or 2 short questions. We have more time after this session anyhow in the roundtable discussion. Yeah?
So you estimate the elevation-dependent troposphere in 5 by 5 kilometer squares. Do you allow that to be completely independent from one 5 kilometer by 5 kilometer to the next one, or is there some kind of a spatial smoother that does not allow the troposphere to change too abruptly? The stratification cannot change too abruptly in space.
Yeah, we do that based on the fact that we expect that the gradient actually is smoother. Also, the underlying model that we are getting this data from, actually, I didn't mention it, but this ETAT product, all these layers, of course, are generated by assimilating data from numerical weather prediction model, total electron content maps, and so on. These all are a coarser resolution, actually. And the topography in the end is the one that modulates this behavior when you apply to it. So we consider that for this area, this was a good trade-off between having a very high resolution gradient and have a good linear fitting, because otherwise you can have more, say, more artifacts, especially if the area is particularly flat. You start to get some zeros and so on. But this is anyway some way that you can manage to do it now. There are some other ways to do it, as some presentations next will show. But in the end, the goal is that you get this layer, and then you don't have to worry to produce it yourself. Yeah.
Okay, thank you. Very quick one. Quick question, quick answer, please. Yeah.
Okay, so to make it very quick, you mentioned you consider adding this gradient, this auxiliary layer in the ETAT, right? What DEM would this be generated on? What DM would this be generated on?
The DM that we are using to generate it now is the Copernicus DEM 30, 90, sorry.
Okay, so maybe some consideration for that. So how about so if we are going to use that as potentially tropospheric or stratification correction, can this create some inconsistencies if we have like very outdated DMs like for open pit mines, etc.?
Sorry, I didn't get the last time of your question. Can you?
So,
louder or maybe
okay, sorry.
farther from the microphone, maybe, or it sounds a bit distorted, sorry.
Is it better now?
I think so.
Yeah, okay. So if you start providing that, this can create quite a lot of inconsistencies for interferometry products that are already using much more up-to-date DEM than Copernicus. Yeah, the gradient estimation can be quite biased.
Well, the good point of providing this this thing in the end is that what you have is a relationship of the height and the tropospheric. It doesn't really matter what DEM are you using, because in the end, when you interpolate your final InSAR grid, let's say, you can even use a higher resolution or even more update DEM coming from a PS analysis. And then you basically use the height of your interpolation point and the relationship of height and phase that you have from the layer, from the tropospheric layer, to actually go to the actual height that your point has, so to say. So it's a way to help you drive your interpolation, but the actual height where you interpolate, it will be the one from your DEM, probably better quality one, or maybe
So,
not.
thank you. I think we have to postpone this discussion. It's important, and I really encourage you all to keep your questions for the roundtable, or maybe even for a coffee break. We are, anyhow, the session chairs are collecting proposals, also for ESA and for the final day. So keep in touch with us and with the authors, and to come to joint recommendations that are accepted by all. In the meantime, I ask the next speaker, Harish Fatahi, to come. Next talk will be given on a similar topic, impact of ETAD-like corrections on Opera co-registered single complex products from Sentinel-1 data. Please go ahead.
All right, thanks. Good afternoon, everyone. So I'm gonna sort of continue. By now, you know, I have two acronyms, ETAD, so you know that. OPERA is the project, observation products for end users using remote sensing analysis. My colleague, David Beckert, already gave a talk in the other conference room. Hopefully some of you at least saw that. Basically, it's a project to produce some products at the national and global scales. In this presentation, I'm gonna just talk about one of them, which is the co-registered single loop complex products. And I would like to thank my colleagues, as you see on the presentation. So the product that ultimately is gonna come out is actually the surface displacement over North America. The product has been defined to be frame-wise. We took the burst ID, burst map from ESA, and defined some frames of our own based on the burst IDs. The displacement product is gonna come out over those frames, and they are gonna have around one burst overlap, so around 200, 240 kilometer. But to get there, we know that we have to co-register the SLC images from ESA, so we have these intermediate products called co-registered Sentinel-1 SLC images, which later will be fed to the displacement time series. But of course, we are going to archive them, so the co-registered SLCs will be available to the users too. The algorithm that we chose to do this co-registration is geocoding the SLC images. And basically, it's a geometrical co-registration. Since we are always geocoding to the same grid on the ground, basically, if the geolocation is going fine, then the outputs are going to be geocoded, which is user-friendly, and also co-registered through time. All the developments has been done based on core modules that we have developed for InSAR, actually, in ICE3. And for this need for Opera, we have developed a downstream software called Compass, which the core modules are still ICE3, but the downstream workflow is in Python and for Opera needs. When we have the geocoded SLCs, probably you have seen presentations from Howard Zipker that then the life is much easier because interferometry is simplified to just cross multiplication of two geocoded SLCs, and you get interferograms easily. But the key to get there is really to get to the precise geolocation. If geolocation for each of those SLCs is not precisely done, then they are not co-registered at the end. For Opera, we came up with some requirements to drive the, basically the driver for the requirements and the relative geolocation is interferometric coherence, roughly around 1/10 of a pixel to get to the basically precisely co-registered in terms of the quality of the phase. The products are gonna be over grids of 5 by 10 meters pixel spacing over UTM grids. They're gonna be provided in HDF5 files with CF conventions, GIS friendly. You can just open it in a QGIS software and the geolocation information should be understood. And they're gonna be available, I think sometime in October, hopefully will come out from ASF TAC. I'm just showing a screenshot of the of the structure of the product. And you see that one of them is burst ID, basically, because the product is burst-wise. We take one SLC save file and we produce all the geocoded SLCs. So each product is one burst. And that's another advantage, that the life of the users will be very easy if somebody just want to process one product so they can pull the entire stack of the geocoded bursts. And we are storing whatever correction that we are doing for producing those geocoded SLCs. But again, the key is really to get to precise geolocation. And as Victor told us already, there are many contributors there to get to the precise geolocation. There is a tropospheric range delay, which for this product, we are actually using the same model for TerraSAR-X. So we are not going with the atmospheric models because we have a very short latency on producing the product, and we did some analysis to meet the requirements in terms of the geolocation. Just the static model is good enough. For ionosphere, however, we are going with the available GIM models. On the IGS website, they are available, but we are pulling them from the DAC. So that's the ionospheric range delay. And then we have all these different ETAD specific Sentinel-1 processing timing corrections that we don't have them. So for this product, we went ahead. Christoph Giesinger and colleagues here, they have written a very nice paper and a very nice ATBD. So we looked at the details. We basically implemented whatever we needed for the timing correction. One of them is the biostatic delay, for which the processor for Sentinel-1 is doing only an approximation, but then they recommend in the paper to do actually a better and a range-dependent biostatic delay. So in this equation, we are taking out what was applied during focusing and apply what they recommend as the more precise way. And then there are other corrections that, as Victor showed, the results, the details are in the paper. One is the Doppler shift. That's, if you have the zero Doppler strip map, it's not a big deal, but with TOPS already, Poprad and colleagues, Christoph, they have shown that actually it does matter for TOPS, so we have to take care of it. And then we have the azimuth FM rate mismatch. The problem is that the FM rate of the the processor from ESA currently is using is getting updated very slowly, with a rate slower than somewhere when we have significant topography changes. So basically that results in an azimuth FM rate that is not consistent with what it should have been. Basically the true FM rate would be different. So we can just compute it, and based on, again, the work from our colleagues, we can just compute it and account for it. So with all those corrections, plus solid earth tide that I didn't mention also, is we have a model for solid earth tide, so we just use that on an existing software. So there is validation sites chosen for CSLC for Opera. There are sites with corner reflectors. I think the main sites is gonna be still Rosemont in California. But then there are sites with new corner reflectors that Opera has installed, or a couple that NISAR has installed, NISAR project. And there are sites, those red boxes, that we do also validate, not with corner reflectors, but by running cross correlation and through time looking at the residual offsets of the geocoded SLCs. Here are some preliminary results. The validation is ongoing. The validation team actually is different from the algorithm team that I am responsible for, but all working together. Some preliminary results on our side that shows to see if we can get close to meeting the requirements. On this plot, I'm showing the first plot basically on the left side is the impact of biostatic delay. And that could be a couple of meters, 1, 2, 3 meters actually. So that's significant on the absolute geolocation. These are the results from corner reflector, one of the corner reflectors in Rosemont. The impact of azimuth FM rate over there was not significant, at least centimeter level. So in the plot, I don't see it much. Clearly on Doppler shift, similarly, it was not significant here. And the environmental impacts, troposphere plays a significant role, as you would have guessed, because we have 2-3 meters tropospheric delay everywhere, and just projecting it to ground range is like 4-5 meters, and that's what you see on the left plot, that if we don't correct for tropospheric delay, we are about 5-6 meters error of the geolocation, and when we correct for troposphere, we are getting very close to the zero. Ionosphere around probably half a meter or so in roughly we are getting improvement just by applying ionospheric delay. And solid earth side is smaller, but that's also some centimeter or tens of centimeter that has been documented in the publications before. So if we look at all the corner reflectors in Rosemont, all the stack of the data that we have for 2 tracks, ascending and descending. Here is the final results, average and standard deviation over different dates. The blue shows if we don't do any correction and geocode SLCs and then estimate the geolocation errors. And orange is what we get preliminary results because validation is not done completely, but very clearly that the geolocation improves significantly with the ETAT corrections algorithm plus those ancillary data, ionosphere based correction that we are doing, and also static tropospheric delay. The other validation approach is basically looking at the range offsets and azimuth offsets, or offsets actually in X and Y direction, north and east direction, because we have geocoded the products. Work from my colleagues, John Blue and his team, that they are looking at stacks of geocoded SLCs, run amplitude cross correlation, and look at those residuals. Overall, we are within the requirement, but some interesting work is going on there. What we are missing, traditionally we have always looked at the corner reflectors in range Doppler. So we don't have the DEM error usually there because we know the height of the corner reflectors precisely surveyed. But here we have geolocated the SLC. So whatever DEM error we had in the DEM is already there. So whatever geolocation residual we have is actually impacted by the DEM error. That's one contribution. Ionosphere, well, we are not accounting for the azimuth part of the ionosphere. That's what Victor mentioned that they are working on, and we have also done some work there. Yes, there are some contribution, but not big enough to impact our requirements. Ionosphere in general, the model could be inaccurate to some extent. 240Q usually our colleagues on the GNSS tell us. And then there is topside tech. We are not accounting for that for this project. And tropospheric residuals, because we are using a static model all the time, we use the same model, so we are not taking into account the variation of the troposphere, and that could be 20-30 centimeter. And just the peak estimation itself, it could be actually some uncertainties there. So some results, we were able actually to geocode SLCs. Here is one example. that we geocode each burst SLC, and then we make interferograms and stitch the interferograms, and they come out very nicely. We don't see any burst discontinuities at the burst boundaries, which tells me that the azimuth geolocation has gone through nicely with all those corrections, and that's very promising. Actually, our data system scaled to the globe. Sorry, not to the globe for this one, to the national scale for one test case so far, and that was very promising. And we looked at many interferograms. They all look very reasonable, no significant burst discontinuities in the interferograms. We had a student intern. We were wondering, since we have traditionally done InSAR displacement time series analysis in radar coordinates, is there any different if we do it actually in the geocoded coordinates? And you see the results on the left is what we have done traditionally over Houston area. And on the right side is what we get from geocoded SLCs. And if we look at the differences, actually they are very, very similar. Sub-millimeter per year difference. And we have compared, basically run through the geocoded SLC, feed it to the displacement time series, and compare with GPS, and we get around 1 millimeter per year accuracy. Am I out of time?
No, a couple of minutes, but...
Okay, yeah, 2-3 more slides. So, yeah, this is exciting. If we compare the displacement, rate of displacement time series over Mojave Desert, that it's all with geocoded SLCs and compared with GNSS, completely independent. We have done nothing to force the two to fit together. We get to 1 millimeter per year, but this is the state-of-the-art algorithm that we have. And we have a presentation, actually. My colleague Scott Stanowitz and Sarah Mirzai have a presentation, I think, on Wednesday. And we have one poster, too, on the algorithm, if you are interested. The same algorithm, the same corrections we have applied to RTC product. My colleague Franz Mayer from ASF is going to have a poster on the algorithm for that one as well, on the validation results. But a snapshot, as David also showed, very exciting that things are scaling up and the quality looks good. One caveat on the burst ID, I already told, we have been in touch with Morial. We have a solution, but the problem also came up this morning, was reported by ESA colleagues. And that was the ascending node time in the metadata of the SLC that we really needed to be very precise. And there is inaccuracy of a couple of seconds, very rare, but if they exist, they would cause these kind of issues. Basically, we are relying on those burst IDs heavily for the Opera project, and that's why I was insisting this morning that I hope that they will be reproduced. But anyways, we are currently not relying on the annotation for deriving the ascending node time to get to the burst ID. We computed in coordination with Morial. We are basically looking at the orbit and determine what should be the ascending node time. We did an analysis globally over 2021, and we concluded that actually it's very rare, but still we want 0 errors. So because we don't want to affect our time series analysis. And yes, we have to fix that. We will make that recommendation anyways, because without that, this burst ID determination is going to be a little bit problematic, and that would be the result on the left. But if we fix it, it's on the right. And for Opera, anyway, we have a fix. In summary, I hope that I have told you that we have developed a workflow to generate the co-register single-look complex images in geocoded domain. The results of the geolocation are very promising to meet the requirements. And that's thanks to the ETAD algorithms here. We don't have the exact product, but we have the algorithm and we have used it extensively. We don't see really burst boundaries in the sample interferogram so far, so that's promising. And the InSAR time series in the geocoded SLC domain looks very promising too. We see differences very small compared to the traditional radar coordinates, even at the PSDS level. And comparing with GPS also is very promising. Thank you for your attention.
Thank you very much, Harish, for this comprehensive overview. We do have time for a short question. Hi, sorry.
The comparison, what you showed for, I think it was Houston or Dallas, it looked to me that the geocoded, the InSAR from the geocoded SLC had less holes. Is it right? Is it related to the resolution?
Oh, this one?
Yes, so the left one, the radar stack is...
Oh, no, it's just the boundary of the two were not exactly the same, so...
No, I mean, well, some areas where I look at, there's, on the left side, there's more holes than on the right side.
On the left side, okay.
Okay, sorry. The radar
Right.
stack is having more holes.
Don't over-interpret this, but yeah, we're exactly. I mean, they have gone through two different chain of processing by a student, so we are still evaluating, but overall, the difference map, what important is those pixels that were common between the two, which I think overall, I don't see much holes. I think overall they are consistent.
No. Ah, yeah. One more question. Most.
Hi, thanks very much. Your Mojave example, it might be a bit unfair if it's someone else's work, but I thought there were still burst discontinuities in the Mojave example of the time series velocity.
I am so sorry, you have to repeat it.
Slowly, please.
The Mojave Desert. Mojave.
Oh, Mojave Desert,
Mojave.
okay. All right, so what's the question?
I see burst discontinuities in the northeast corner.
Yeah, okay. That's much better.
Sorry.
Yeah, there could be. So, and the could be due to the reasons that I just documented. That yeah, we are not taking care of the azimuth for ionosphere, for example, or those corrections could have some uncertainties. So no data-driven corrections have been applied here. But yeah, it doesn't bother me.
Okay.
No.
Yes.
Relevant are all these corrections for NISAR or Roselle, for example?
Oh, very relevant. We have a product called Geocoded SLC for NISAR, which probably you have heard about it. And over there, the biostatic delay, we are already taking into account precisely as you guys suggested to do in first place. So it's already built in. So we don't have that approximation. For ionosphere, we are doing a little bit more than what we did here because for NISAR, it's L-band, it's 20 times worse. So we have to take care of azimuth, we have to take care of topside tech and all that. Troposphere, we are using the same static models. So at least at that level, they are very similar.
So, fine. Let's move on. Thank you again. The next talk will be given by Riccardo Nanari for his team, exploiting the ETACT product for estimation and filtering, help me, phase screen filtering of medium and high resolution InSAR products. Got it.
Thank you very much, Michael. Okay, so good afternoon, everybody. As Michael said, and as you can see from the title, my talk is essentially following the lines of what you have already seen with the first talk, so I will benefit from many of the things said by Victor. The rationale is the same. What we want to do is to see what's going on if we can mitigate atmospheric phase artifacts in differential SAR interferograms, but also in, let's say, more advanced differential products. But that's the base. And in particular, the focus is on full resolution or even medium resolution. So I'm talking about interferograms at, let's say, 30 under meter resolution. Okay, so here is a brief outline of the presentation. I will start really very briefly with an introduction. The data, as I said, it has been already explained twice, so I can go fast, and so we can save a little bit of time. Then I will go a little bit in details again about what I mean when I say that if you use the actual EDA data and you look at high resolution or medium resolution differential interferogram, you see artifacts when you try to use the EDA data to correct the atmospheric phase screen. Then I will show you a solution that we have developed that is mostly focused on multi-temporal interferograms, mostly on the S-bus processing chain that we have, but in general I would say a multi-temporal differential interferogram, although it seems to work rather nicely also with single interferograms, and then some concluding remarks. Okay, so we are dealing with this auxiliary data, I would call them, this extended timing annotation data set that, as you heard, essentially have been developed mostly in order to improve the timing, the range and the azimuth timing of our Sentinel-1 SAR image, in particular of those acquired with TOPS mode, and the characteristics are too. These information are available at burst level, and we have them at 200 meters resolution. So there is, let's say, downsampling with respect to the full resolution, more in range than in azimuth. This is the list of all the EDA correction. I don't go in the details of this. There is this nice Kissinger paper where you can find details. I will concentrate on these three layers, which are those interesting for us if, let's say, the target is to try to use this EDA information also to mitigate the atmospheric phase effect. So it's tropospheric delay, ionospheric delay, and tidal displacement. Actually, there is also an internal calibration information too, so there is a fourth one. Okay, so how do we exploit this data if we want to mitigate our atmospheric phase artifacts? It's rather simple. You already heard, let's repeat quickly. We interpolate this data because, as I mentioned before, they are at 200 meters resolution. So essentially, you can use bilinear interpolation. It's in the notes of the EDA data. Then, once you have interpolated your information, you have to account for the fact that this information, and this is very important, are generated on a single base relevant to each image. So they are generated for the image 1, for the image 2, for the image 3. So essentially, they are on the azimuth range grid of that image. So if you want to use to correct your interferograms and you have a data pair, you have to co-register the correction which is relevant to the secondary image with respect to the master one. And this correction is just computed by taking the tropospheric correction plus the tidal information minus the ionospheric correction plus this internal calibration stuff. And then if you compute this for your master and for your secondary image, then you subtract, you have your correction for the interferogram. Actually, Ivana, that should do it, the presentation instead of me, discovered that you do not have to subtract as we expected. You have to add. Okay. But before adding, you just need to convert in phase, and then it's done. You have your correction. Okay, now let's see with some example what happens if you apply this procedure and you try to correct your interferograms. So let's consider this data set. It's a significant data set. You see, it's 1 year of data, 34 images, relevant to a zone that is from central Italy up to southern Italy. So it's a rather significant portion of the country. Okay, so if you go straight forward and if you look at your interference, in this case, I'm showing all products at 80 meters by 80 meters. If I would show you product at full resolution, everything you see now will be much more emphasized. On left side, you have the original interferogram, the one that you compute from SLC data. on the left, you have the correction that I have computed for this interferogram exactly as I have shown before. And if you subtract, okay, essentially everything seems to work nice. In this case, I selected an interferogram where you clearly see a fringe reduction, so it seems to work, and here is another one. So everything at 80 meter by 80 meters seems to work fine. Now the problem came, and that's what Ivan again discovered, I think more or less one and a half year ago. If you zoom in your interferogram, then the situation is a little bit more complicated, because you see I selected this zoom. This is the most beautiful place of the world. This is the Napoli Bay Area where I live, okay? In this beautiful place, you see there is Mount Vesuvio and Sorrento Peninsula. So if you zoom on your corrected interferograms and you give a look to the topographic area of Mount Vesuvio and Sorrento Peninsula, you see there are these artifacts where you even can get more than one fringe. And so we were very surprised when we saw this results in our correction. So we discussed with the rest of the team, and finally what came immediately after was that the problem was inside the tropospheric correction. So these little artifacts, you see the Vesuvius, for example, are in the tropospheric correction, not in the ionospheric, not in the tidal, in the tropospheric correction. And why there is this problem? Because let's go back to the original decision. Everything is computed on a single image base. So I have the correction of image 1 on the azimuth range grid of image 1, and then of image 2, of image 3. And the problem is that each image has its own grid. So now, if you compensate this in terms of alignment of co-registration, but intrinsically the phase which is related to the topography is on this grid, you have these artifacts. Okay. So the artifacts are within the topography, and this is very easy to verify because each ETAD product has also this topographic information generated in the azimuth range grid. So the troubles come from the tropospheric correction and are in the tropospheric correction because of the local topography. But then we thought, okay, this is the problem, but if we look then carefully to the problem, it's not that complicated, because if you have a stack, in this case 30 images, you have also a stack of 30 DMs that you can co-register. And if you look then of your sequence of DMs, you can compute the standard deviation of your DM, so you can immediately identify from your standard deviation which are the pixels that are affected by these artifacts. So you know where the artifacts are within the native ETAD data, and you also can correct, because you can average already with 10 images, let's say, this flickering that is coming from this different grid is mitigated. And so basically, with the internal information that you have, the idea is that you can correct this problem. What you can do essentially is to go back to your tropospheric correction. Through the standard deviation, you masked out the pixels which are characterized by artifacts, and then by taking into account the locally your relationship between the topography that has been correct due to the averaging and the tropospheric information is linear. Through this local linearity, you can correct your tropospheric effects. And you can come out image by image with a tropospheric correction directly using the information internal to the ETAD data. And it works really fine. You see on Mount Vesuvio and the Sorrento Peninsula, left side the original, right-hand side the new one. The subtraction is zero mean, only the artifacts are there. And so you can go back to the regeneration of your tropospheric correction for each image. This is for 2 images of the original interferogram, and then now the artifacts are gone, because essentially we have corrected the sources which is relevant to DM. And this is basically for the interference, it's straightforward. Here is another interferogram with the artifacts. We apply the solution I have described, and the artifacts are gone. And this is for, I think, 120 interference we have generated with this 34, no, probably there were 90. Okay, so let's say, our feeling is that, okay, we have been upset when we have seen these artifacts, but there are already within the ETAD information all the information to correct this effect. With a time series, what's going on with interferometric data pair, because in some cases we are using interferometric data pair. Clearly the situation is a little bit worse, but it's still possible to apply the same logic. Clearly in this case you have two images, so you have two DMs, so you cannot generate the standard deviation, but you can compute the amplitude of the difference. And from the amplitude of the difference, most of the areas characterized by artifacts you get, you average your DM with 2 DM, not with n. Then you go back to your interference. It seems correct. Actually, this is on the left-hand side, the correction with 2 acquisition, on the right-hand side with 34 acquisition. If you look into the minus pi interval, the difference is 0. Clearly it's not 0. If we zoom a little bit, there are details, but these are fraction of a fringe. So this correction, and this is for several interferogram, let's say it's quickly converging. So you don't need so many data. It's rather self-consistent. So what we are doing now is essentially to try to understand if we can operationally then use SDR data without other correction. To do this, we are making tests with our ground motion system at the national scale. In particular, we are starting from some acquisition patches, like the one in the Napoli Bay area. The idea is essentially to make a full statistical analysis, essentially to look at our stacks with the ETAD correction, without the ETAD correction, giving a look to the phase standard deviation, if it is reduced or increased, to the correlation between the unwrapped interferometric phase and the elevation, and even more sophisticated to the variograms evaluation. Because variograms, as you heard before, gives you information about a couple of pixels at different scales, at different distances, so it gives to you broad information on the interferometric standard deviation. And the first results are good. Of course, Ivana and Federica gave to me only good examples. There are also bad examples. They are listening me. So, but let's say the results are very promising. You see, for example, for what concerns the correlation reduces, essentially the dependence on the topography. It reduces, and also if you look at some variograms, you clearly see in many cases a reduction. Clearly, the analysis is still in progress because we need to be 100% sure that everything is okay. But once again, first results show that after this correction, this ETAD-based data can be used even for medium and full resolution interferograms at a very successful and with a very simple correction procedure. Okay, this brings me to the conclusion. So, as I showed to you, and shown also before, if you work with present-day ETAD products that are going to be delivered at the end of the year, as we heard, and you generate interferogram and medium and full resolution, you use just straightforwardly, you can have the risk of having artifacts at full resolution, very significant. These artifacts are due to this different grading which is on the computation of image by image base of the single correction. But the solution I have presented without essentially changing anything, but just considering the multi-temporal information availability allows to correct straightforwardly the ETAD correction. The correction is not nice, but it's the message. And even with a limited number of images, this seems to work nice. Even for single interferogram can be effectively used. Our experiments show that it's really, in many, many cases, enough, a data pair. And let's say the work is in progress for making a full assessment at the national level, so to produce a report that clarify, let's say, in our mind, 100%, which is the limitation or the effectiveness of this kind of a correction without the ground motion service we are developing for Italy. Thank you very much for your attention.
Thank you very much, Riccardo. This seems to be, was definitely an alternative approach for corrections, and you pointed out, and I want to repeat again, we are talking about the current version, and hopefully from what Victor explained, the future version of ETAD should not require this kind of correction at all. Just because scientists tend to be so enthusiastic on correcting and new algorithms, but we hope that this should be not necessary or could be further improved. We will see. Other questions on this talk? Charles, yeah?
It's very interesting, and it seems a very practical solution to the problem. I was wondering if you could store also in the ETAD grid the slopes, the first derivative basically of the atmospheric correction or the different factors, and that would be an alternate solution to solving this problem of having the errors in the DEM where it's sampled. So that basically using the derivative information, you could interpolate the result more effectively with height.
Charles, I would say that the problem would not come out if we would have a reference grid. Okay, if everything will be generated originally from a reference grid, like the one shown by Hirsch, there would be no problem, okay? The problem comes because of different grids. Now, once you have this clear, the signal, the tropospheric component locally is very simple because it's a constant, plus B, another constant, times Z, the local topography. Okay, so you have to estimate 2 parameters in a little box. If you exclude in your block what is wrong, and then getting an estimate of 2 parameters for each pixel is really like eating a piece of chocolate, you know. So the problem is very simple. The important thing is to kick out the wrong data. That's the reason why we explored this idea, because probably there is no need to change anything. The problem is so simple once you have identified that it's enough. Of course, you can put more sophisticated information there, but it's so simple, the problem, that I don't see this need. Of course, if there is much more sophisticated information, we are glad, but at the moment, it seems already enough information to use what it's already available. You're welcome.
Maria, do you have a question?
I just want to say that, in fact, providing the slope is what we plan to do in the future, as Victor showed in the first presentation, but this is not something that's happening tomorrow. No? So the current plan is that this is going to be available probably at the end of next year. So in the meantime, I think it's very nice that Riccardo has this kind of solutions also that you can also estimate, like Victor was showing. So it's very important that we have the solutions that we can use before we implement something in the product itself. And so we are very thankful for this kind of propositions. And I just want to take the chance again for thanking you for participating in the pilot and pointing out these artifacts and carry on. And just one short question. I mean, it's a confirmation, but I imagine that if you really demonstrate that you can use this operationally, I imagine that you would recommend that we would make available the entire archive, or what is your recommendation in that respect?
Of course, my recommendation is the entire archive, definitively. Where is Folk? Folk, do you agree with me?
Thank you for the recommendation.
Okay.
Okay, I think we move on. Riccardo, you want to take over?
Yeah. Okay, so we move on with next presentation. Okay. You are fine. Okay, like in this case. Okay, that is going to be given by our colleague, Failing.
Okay, hello everyone. I'm Fei. Today I'm going to talk about, sorry.
It's a little bit tricky. If you do this, you suffer. You have to point there. Okay?
Okay, go back.
Back and forward.
Okay, sorry, from the beginning. Hi, I'm Fei. Today I'm going to talk using InSAR time series to capture the intra-slab earthquake deformation. I would like to first briefly introduce the content of my presentation. I will introduce why intra-slab earthquakes and our study area in northern Chile. Then I will talk about the InSAR data processing regarding the tropospheric correction and ionospheric correction on the improvement of quality of data. I will particularly discuss the ionospheric correction and compare the split spectrum with the code correction. And with all these corrections, we successfully retrieved the concise deformation field using the ICA and do the earthquake source modeling. And later, I will discuss the role of the velocity structure in the intra-slab earthquake detection for future work. So let's first begin from the introduction. Earthquakes are divided into several catalogs based on their location and depth. Events that occurred in a subducting plate are called intraslabs. Normally, intraslab earthquakes are quite deep, ranging from 40 kilometers to over 1,600 kilometers below the surface. So why do we care about the intraslab earthquakes? Not because these intraslab earthquakes can pose great dangerous threat to the human society, but also their rupture mechanism is not fully understood. In addition, intraslab earthquake also inform us the geometry and orientation of the stress within the slab. Within the slab and providing insight into the property of slab, such as the temperature and phase changes. However, for the earthquake at such depths, we heavily rely on the seismology to study them. Luckily, with the advance of geodetic observation, especially InSAR, we are capable to measure the Earth surface deformation at millimeter level, providing alternative way to study these intraslab earthquakes. Currently, the majority of InSAR-based earthquake studies are shallow events whose depths are below 30 kilometers. And for the intraslab earthquake, they are rarely the focus of InSAR-based work due to the efforts required to retrieve their concise deformation field, retrieve their concentric displacement from the noise, therefore leaving a research gap in this area. So I choose the subducting zone in northern Chile as my study area. Here, this figure, the left-hand side figure, shows all the historical earthquake events, magnitude about 6.0 since 1976, where the precise seismic network was established. And you can see the earthquake depths gradually increase as we move into the slab. And I choose these 6.8 earthquakes occurred in 2020, whose centralized depth is 112 kilometers, according to the USGS as the study case. Interestingly, there are several GPS stations near the epicenter of these events. For example, the SP80 station, labeled by the yellow circle, and you can see their GPS time series capture the coseismic offset, but in all directions, the cosine offset are less than 10 millimeter levels. So the question is, can we observe this cosine deformation intraslab from the InSAR? So to answer this question, I have processed 4 years of Sentinel-1 InSAR time series spanning January 2018 to October 2021 over a large area to increase of chance to capture the causative offset. So here's my workflow regarding the InSAR data processing. I generate the interferon using the iSolver, doing the multi-looking but low spatial filtering. Then I do the ionosphere correction, including the troposphere correction and ionosphere correction by geckos and split spectrum respectively. And finally, I use the stems to do time series. So here shows a typical example of about the atmosphere correction on ascending. So this figure shows the original interferogram, the ionospheric delay derived from split spectrum, the troposphere from the geckos, and all the corresponding corrected interferogram. As you can see, the long wavelength signals are greatly reduced after doing all these corrections, suggesting the improvement of the quality of data. So I have evaluated how the ionospheric correction could improve the quality of data. So this figure shows the standard deviation change after doing the ionospheric correction. So the x-axis shows the number of epoch, and the y-axis shows the reduction of the standard deviation after correction. So above the zero value baseline suggests the standard deviation reduction, which means the data is get better. So you can see for the ascending, the quality of data is greatly improved. While for the descending, the data is even worse after doing the ionospheric correction. So this mainly due to the different acquisition time. The ascending data is acquired at 6 p.m., which has much stronger sun activities compared to that of ascending acquired at 6 a.m. So therefore, the ionospheric delay on the ascending is also much stronger than that of descending. And I believe the split spectrum, the performance of split spectrum should be the same for both tracks. However, the algorithm is not sensitive enough to capture the minor ionospheric delay on descending, making it slightly worse after doing the correction. So this table shows the quantitative way after doing all these corrections. Please do not bother to read all these numbers. I just want to say that after doing all the troposphere correction and ionosphere correction, the quality of data are greatly improved, and they are crucial for the subsequent earthquake, intraslab earthquake detection. So we also, to compare the different algorithm of ionospheric correction, we apply the vertical total content product of the Center for Orbit Determination in Europe to do the ionospheric correction on our data set. Here and after simply referred to as code. So we reproduce the algorithm and code, which achieved the exactly same result as the ETAD ionospheric delay. So basically here we are comparing the split spectrum with the ETAD ionospheric correction. So as we can see from the figures, the split spectrum does improve the quality of data on ascending, which average about 14% standard deviation reduction. However, still less than the 33% by the split spectrum. While for the descending, both corrections failed to reduce the noise. However, the code corrections show some seasonalities and perform slightly better in the winter. So this figure shows a typical example comparison between the split spectrum and code correction. It shows the red phase here for the better illustration. So you can see that the phase gradient, the direction of the phase, are same for the split spectrum and the code. However, simply the density of the code is less. So therefore, so basically the code underestimates the ionospheric delay and therefore is less effective than the split spectrum in our case. So if you want to know more detail regarding the code correction, please check my colleague Radar's poster ID 140 tomorrow. So let's move to the second part of my workflow regarding the earthquake, intraslab earthquake study. So first, we consider the deformation model associated with the seismic circle. So the equation here The H stands for the step function. T0 represents the earthquake event time. C is the coseismic offset. Since we do not observe clear post-seismic deformation, we do not consider the post-seismic deformation field here. And we also use a sine and cosine function to fit the seasonal term. V is the long-term linear deformation rate, which contains part of the interseismic rate, and B is the constant offset. Based on this deformation model, we applied two different approaches to retrieve the coseismic deformation field. The first one is called parameterized fitting, which basically fit this deformation model to the InSAR time series pixel by pixel and solve the parameter C here to reconstruct the coseismic deformation field. And another approach we recently used is the independent component analysis, ICA, to better retrieve the coseismic deformation field. And we also use this deformation model to scale the deformation pattern. And finally, we do the earthquake source modeling using the base software within a layered half space, combine InSAR and GPS to do a joint inversion. So this figure shows how we retrieve the coseismic deformation on ascending data. The most left-hand side panel shows the forward modeling using the source parameter from the USGS. So this is basically a prediction of how the surface deformation looks like from the seismology. So the bottom panel shows the reconstructed deformation field from the parameterized fitting and the corresponding time series on the peak displacement signals. The fitting curve is indicated by the red dashed line, and you can see the cosine offset as earthquake event time, which indicated by the vertical green dashed line. And also the other approach is we're using the spatial ICA to retrieve the coseismic offset. And the main panel shows the deformation pattern, and also the time series panel shows the corresponding column in the mixing matrix. This value represent the weight of this deformation pattern in each epoch. So therefore, they also can be fitted by the deformation model to solve the so-called coseismic offset to scale this deformation pattern to achieve the final product of the coseismic deformation field. We can see that the ICA did a better job, generate a much cleaner coseismic deformation field, and also greatly reduced the noise in the far field. And we therefore use this deformation pattern retrieved from ICA to do the subsequent earthquake modeling. So this figure shows the modeling result using the combining both InSAR and GPS. The left-hand side panel shows the observation, the synthetic, and residues of the downside of the InSAR data. And okay, the right-hand side shows the GPS modeling result. Overall, we think the model fits the data quite well given the small magnitude. So this figure shows the posterior distribution for the some selected source parameters. Overall, they agree well with USGS solution. The discrepancy regarding the rake value probably is because the strong motion recorded by the GPS, which suggests there might be considerable slip in this direction. So what can we learn from this case study regarding the intrastellar earthquake detection by InSAR? So one very important factor we rarely consider when we study the shallow events are the change of rigidity value. So if we look at the equation, the seismic moment calculation equation, if for a given magnitude or moment, larger rigidity value means smaller deformation area, also or smaller average slip, which in other words, smaller surface displacement and harder for InSAR to detect. The left-hand panel figure shows the increase of shear modulus with depths under Lawson Chile. So we can see the shear modular great increase from 30 gigapascal to around 75 gigapascal in the mantle. And we use these change of shear modulus and also the velocity structure under Lawson Chile to generate the right-hand side panel. Basically, these are the predict the peak displacement for the earthquake magnitude range from 6 to 8, that's from 0 to 300 kilometers. And we believe that for the deformation peak displacement about 10 millimeters, they could be detected by the InSAR. And for our case study here, is just barely detected. So here's the final some take-home messages. Allospheric correction on Sentinel-1 ascending data can greatly improve the quality of data in low latitude region, but it's probably not worth doing on the descending track data. We retrieve coset deformation of an intraslab earthquake with peak displacement around 6 millimeters using InSAR time series. And finally, InSAR could help to constrain the fault geometry of intraslab earthquake and compensate seismology for future work. That's all. Thank you for listening.
We have time for a quick question. Folk, can you keep the microphone?
I have a quick question regarding the earthquake. Any indications for post-seismic deformation?
Yeah, we don't observe very clear coset deformation, both in the InSAR and the GPS. So we simply do not consider them in the deformation model. Yeah.
Sorry, there is or there is none?
No. Yeah.
Hersh.
Nice presentation. So on the plot that you showed the standard deviation after ionospheric correction with split spectrum, maybe one more. Yeah, this one. So the label on the left is significantly larger than the right. So what's your conclusion finally? Are we basically, because yeah, this one is -1 to 1. So I see probably around -1 to 1 on the left side too. So are we within the uncertainty of the ionospheric phase estimates here? Is that your interpretation? And basically my comment, if you are using guys, I would say we probably have the ionospheric uncertainties. I don't know if you have looked at those and whether you can confirm that.
Okay, so I think the standard deviation of the allospheric deviation from the ice also has its own certainty. I think it's quite large. Yeah, and for this comparison, because like I mentioned, the allospheric data on the ascending is much stronger, so the standard deviation also stronger, and also therefore the correction also much bigger regarding the scale. Yeah.
Okay, thank you very much. Okay, so we move from earthquake to volcanoes. I invite the last speaker, Lin Shen. Welcome.
Good afternoon, everyone. I'm Lin Shen from University of Leeds. So in today's talk, I'm showing you work on developing a database of deformation at global volcanoes for machine learning applications. And this work is funded by the DeepWork project, which is led by Professor Andy Hooper. And I would like to thank all of my colleagues for their contribution. So as we know, the deformation of a volcano surface due to magma migrating beneath is a key indicator of ongoing and potential volcano activities. And different from satellite monitoring of some volcanic gases and small imaging, such as which is mainly dominated by the detection of core eruptive emissions. The satellite measurements of deformation using InSAR also include a high proportion of inter- and pre-eruptive signals. So here, the figures on the right-hand side shows the 3 Sentinel-1 intervalograms with pre-eruptive signals leading up to 3 eruption events over Reykjanes Peninsula of Iceland in March 2021, August 2022, and also this July. So we can find out that the satellite measurements of deformation using InSAR is a good statistical predictor of eruption within given time intervals. And although the InSAR has been applied to measure volcano deformation over the last 25 years, it is only now that InSAR can be considered a possible monitoring tool for volcano deformation due to the launch of multiple missions, including Sentinel-1, which allow the data to be collected every 6 or 12 days, and also can make the data available within hours. And Comet, here based in UK, has developed an operational system we call SAR for large-scale interferometric processing of Sentinel-1 data. So for the data covering these active volcanoes, showing us the green polygons in the plot, are processed on a short-term base, so can allow the generation of interferograms over all active volcanoes as soon as the Sentinel-1 SOC data is delivered from ESA. So in this work, building up on the SAR system, we have developed an automatic processor to derive the high-resolution displacement time series over global subaerial volcanoes, including the procedure of InSAR processing, time series analysis, and atmospheric corrections. Specifically, we process the interferograms with intercal and pre-eruptive signals over all subaerial volcanoes, including some volcanoes that have never been analyzed before, using improved algorithm to address major limits on the effectiveness of InSAR. And for each volcano, we derived displacement time series in high resolution of 30 meters, which not only allow us to focus on the period when there is large-scale deformation, but also on smaller scale signals that are associated with processes such as local landslides and local changes in hydrothermal system. And all of the process data saved in a developed operational database, which we cropped the area around each volcano during the processing to keep the data storage to be minimum. For all of this data, it will be difficult for individual scientists to extract all the useful information. So here in this study, we also apply the machine learning to extract the information from the data efficiently for the further interpretation, and also help with the future forecast the volcano activity. And the products stored in this database can be generally divided into two categories. The first one is about the metadata, which is processed from the SAR portal combined with the developed volcano info catalog. And the second part is about the deformation products, including the accumulative displacement and also accordingly spatial and temporal information. And this data saved in a database we called VOCNATE, with the neighborhood of the type of deformation and also the location of the deformation within the accumulative displacement for the further machine learning interpretation. And meanwhile, we also store them into a developed Comet volcanic and magmatic deformation portal for online interactive visualization and data request, which I will demonstrate later in this talk. And in the following slides, I will show you the techniques we have implemented in this processor. So when we use the InSAR to process the volcano deformation, the one major limiting factor is that the signals can become decorrelated in areas of glacier coverage, winter snow, and heavy vegetation. So for example, for the volcanoes in Iceland, they are glaciated and also covered in snow during winter time. And here the figure showing derived average coherence for Hekla volcano in Iceland, where we can find the coherence is generally very poor over the peak region of the caldera and also much of the volcanic region. And also in the heavy vegetative and the rainforest region, for example, here for the volcano Nangina in Papua New Guinea, we can also find the general very poor coherence over the most region of the volcano caldera. So to address this limitation, in this processor, we have incorporated coherence analysis by building a coherence matrix. And here, this figure showing the coherence matrix for the Hekla volcano in Iceland, which each of the patch shows the estimate average coherence from the short temporal baseline interval ones between the month A and month B. So for this case, we can detect the continuous good time window from the June to September. And so then we can generate the 1-year interferograms to complement to the short temporal baseline interferograms. And alternatively, for other regions which we cannot detect this continuous good time window, it will be useful to also detect the separate or individual good coherent time months to generate either 6 months or 3 months interferograms to combine with the short temporal baseline interferograms. So this will give us a much better coherent and also highly redundant baseline network of interferograms for the later time series analysis. And in InSAR processing, to recover the correct phase from the wrapped interferograms is also a very significant step. So in this processor, we have implemented an improved phase unwrapping algorithm by first model several sources of phase delay related to the topography and atmosphere delays and also the overall ramp, and then remove them before the unwrapping to reduce the phase gradients. And based on this phase gradient reduced wrapped interferograms, we applied a Gaussian filtering to mask inconsistent region between the original and future interferograms. And to avoid the unwrapping arrows due to the noise discontinuity, we also apply a 2D Gaussian kernel interpolation to this mask region. So the final unwrapping will be based on the filtered and interpolate interferograms to achieve a better performance. And for this erroneous unwrapped interferograms, through a phase loop kosher arrow check, can identify and remove these bad interferograms from the network before the time series. And in this processor, to avoid to remove the whole interferograms with the individual unwrapping arrows, we applied algorithm to identify individual pixels that fill each loop kosher arrow check. And also for those redundant interferograms not in island of loops, we also exclude them as the loop kosher arrow check is not applicable for these interferograms. So here is a figure showing the comparison of the results with and without this pixel-wise phase loop kosher arrow check implement. And we can find that after the removing the interferograms with the phase loop kosher arrow check, phase loop kosher arrow, and the interferograms are not in island of the loops for each point, we can achieve a better velocity field and also with a decreased root mean square of residuals. And for another limiting factor in InSAR measurement, that is trophy delays, we also incorporate a spatial variance scaling method in this processor to improve the retrieval of the volcanic deformation from interferograms by using by combining the use of the high resolution weather mode data and also the interferometric phase itself. So here there are 2 cases shows that the method is effective in the scenario when there is co-eruptive signals and also when there is inflation during the intereruptive stage, and also demonstrate that this processing will not touch the signals itself. And based on the derived displacement time series, we incorporate independent component analysis to detect the change in deformation signal automatically using Lake's alert algorithm. And this algorithm combines the use of clustering and manifold knurling. Here we can show as the 2D scatter plot where we used the T-distribute stochastic neighboring embedding method to find the position of each point and combine with the clustering algorithm HDB scan to give the neighbors for each point. So based on these clustering and manifold knurling results, we can recover the spatial pattern for each knurling source and to derive this time series for each knurling source. And then based on the derived time series of each knurling source, we then selected part of the baseline data to fit with the least square to derive the temporal pattern for each learning source. And then based on the derived temporal pattern, we can detect if there is island signal change during the monitoring stage. So here several examples showing that for the volcanoes, we have processed from this processor and have detected the signal change from their time series from this independent component analysis. And for example, here for the Novo del Chillin in central Chile, we can find this. Here, the top panel gives us the velocity for this volcano derived from this processor, which the volcano is the most active stratovolcano in this region. And the lower two subplots give the time series we can derive from these two black triangles region over the caldera. And both of the time series show that there is a downward trend starting from the beginning of 2015 until the mid of 2019, before it reversed to an uplift trend until summer 2020. And based on the independent component analysis results, we can also detect these signal chains from our time series, which is starting from the mid of 2019. And recorded from the GNSS data from 2015 to 2020, it also demonstrates that there is an uplift event beginning in July 2019. And based on the detected volcano deformation from the independent component analysis, a further application will be used the deep learning to classify the volcanic source. So here, the figure shows the example that we apply a developed convolutional neural network trained with 500,000 Sentinel-1 interferograms, combined with a large amount of synthetic data and also 15 volcanoes of the real data. And here the right-hand side figure shows the classified example from this trained network for the Novo del Chillin volcano, which the network predicts there is deformation with about 65% probability of seal and 34% probability of dike, which we can find this result is quite promising. So we believe that with using this developed operational database, it will make a huge increase in the number of the volcanoes can be used to train for this neural network and can achieve better and more accurate results in the future. And so far, we have already processed 353 subaerial volcanoes worldwide, which show as this red symbol in the map. And among these volcanoes, for the volcanoes we detected the signal change, we find that their maximum displacement rate is in an average of 10 centimeters per year, within an area of between 5 to 20 kilometers. And for the user who like to get access to the data can be easily visualized and also request from the developed COMET volcanic and magmatic deformation portal. So in the portal, you can find out the derived accumulative displacement and also the time series for each point. And also can get a profile of this displacement and also the corresponding data. And to download data, these results can be exported as the CSV format from the portal as well. Yeah, so to conclude, in this work, we have developed an approach to automatically derive the high-resolution displacement time series for global subaerial volcanoes. And based on the derived time series, displacement time series, we provide the database for the use of machine learning to automatically detect and classify the volcano deformation. And hopefully, in the future, it can be used to help with forecasting the volcanic activities as well. The data currently can be visualized and requested online from the COMET volcanic and magmatic deformation portal. And soon we'll share the whole database, including the codes, to the public under an open source. And we also plan to make it available to other relevant projects such as the EPOS and also the global volcano model. Thanks for your attention, and I'm happy to take any questions.
So we have time for questions. No questions. There, sorry.
Thank you. Impressive task performed. And you probably have said it, but maybe I missed it. As you say, how did you overcome the heavy vegetated volcanoes and the seabed reflections on the heavy vegetated volcanoes? Probably I missed it. So.
How do you overcome coherence problems in vegetated volcanoes?
Yes, so it's like, thanks. So it's for the, it's based on the developed coherence analysis. So the coherence analysis can automatically detect the good coherent time window. So can automatically to connect these good coherent pairs of intergrams and then so to avoid to incorporate the bad pairs with the incoherent noise. Yeah, that's our current solution for the incoherent regions. Thank you.
So I understand that the database that you have for machine learning only works for Sentinel-1. If you have a new mission coming, like InSAR, Rosella, how long will it take for you to bootstrap this database? Because now we have 10 years of Sentinel-1 data, so it's very easy to collect all these infograms. So how long would it take for new missions to be bootstrapped in your application?
It means like how to for other like applications is, yeah. Yes, true. So actually, one of part of the not doing part for this project is that we would like to adapt this processor also to other missions as well, because as we know, the TOPS model is like more complicated than the other like the standard models. So it feels like it will be feasible to adapt the processor we currently have already developed to other missions. So it's in one of the like the future work in on our list. Yes.
Okay, thank you very much.
Thank you.
Oh, sorry, Ramo, sorry.
Yeah,
there is another one.
Thank you. Just one question.
Yeah.
I was wondering, you have your detection algorithm to detect an anomaly in your time series. So you must have a significance level or so to decide where the threshold is. So how do you determine that significance level for this type of volcanoes?
So currently we applied like the uniform parameters for all of the volcanoes, and I think so based on the quality check, it can kind of like doing a customized for this parameter selection as well for other volcanoes. But it's like for the currently automatic processing, we just have the uniform parameters for all of the volcanoes in the processing.
Actually, my question is like if you put the threshold higher, you have more false warnings. If you put it lower, you have more misdetections, basically, right? So you need to determine somewhere where you put that threshold. And I was wondering what your rationale is.
Yeah, so for choosing these parameters for the current uniform scheme, we tested our approach on different regions and to achieve like the kind of like acceptable parameters for all of this data. Yeah. Thank you.
Okay. Okay, now as you heard, we have this 3 hours and a half round trip discussion. I'm joking, it's 30 minutes.
We're back to 25, actually. Round table, we don't have a round table. We have no instructions, but yeah, we have to give recommendations. And this is a chance to stay here, to bring your ideas, to further discuss if needed, not too long. Do we have any, from ESA, any expectations how to proceed? Otherwise, there is scheduled a round table discussion. 30 minutes, it's reduced to 25 already, before we get a cocktail. We have a few questions, but yeah, I think it's also opportunity. Do you have questions prepared already, Giovanni? No. We made a few notes. Yeah. What you showed us? Do you want to start with? Not with contents. A question that I collected earlier was, what else is needed? Is this products and methods we saw so far, is it sufficient? Did we miss anything important, like atmospheric sensors on future missions, or any comments on the methods, things that should be done? I think this was the intention.
If there is no comment, you cannot complain anymore. There. There.
You can use this one.
Hi. So just a question regarding data correction. So do we have already
Louder.
regarding data correction? Do we have already an estimate of the time needed to provide this correction? So will be provided together with the delivery of the SLC image after 1 day. So this is something that I think it could be quite important for a continuous monitoring project with Sentinel data.
Can you keep the microphone to Muriel?
Muriel, did you understand? Can you answer?
Hi. Yeah, so currently the latency of the product is actually determined by the precise orbit, so it would be 20 days, which is the latency of the precise orbit. So this is the current baseline, which is being used right now to produce this data in the ground segment. So this is, let's say, the current status of the data which will be disseminated by the end of the year. However, in the study that we are currently having also with TLR, we are also using on ways to provide solutions with shorter latency, also thinking on applications which eventually need something a bit closer to near real time, or at least with a latency shorter than this 20 days. The idea is that the restituted orbits already have an accuracy that it's good enough, especially for InSAR. It's of course not so important. I mean, in terms of the actual accuracy that we have of the outstress, it's sufficient for some applications. So we try now to look at the other components now with the ionosphere and the troposphere. What are the solutions that we could have to bring this latency down, if not for the official ETAT, but for, let's say, a near real-time version of it. But this is also for the future, and it's now being looked at in the study that we're currently having.
Yes, over there.
Yes, thank you. I think the idea is to come up with recommendations for ESA, right? And so I may have three concepts maybe for discussion. So the first one, given the discussion that we had on the RFI correction, then I think there is an option either to recompute or do a correction on the whole archive. And I think this thing comes up more often, right? That we come up with some problem later on during a mission and then we need to change. So my first recommendation is that we would share methods and algorithms rather than data, right? So that we don't need to recompute a full archive and wait until the whole world is done, but simply share the method how to make that correction so that individual users who want to make a certain correction can do that. So my first recommendation is let's focus more on sharing methodology, software to do things rather than to reprocess data. The second recommendation that I have is to try to have as a general rule that all corrections are reversible, all right? So that we do not make any irreversible corrections. So that if you want, you can always go back to the original data before a certain correction has been made. I think that's also a quite high-level recommendation, and it's up for discussion here. And the third recommendation I would like to give is coming back to a discussion we had several years ago on the orbital tube of Sentinel-1. And that is when Sentinel-1C will be launched, maybe to dedicate a certain part of the mission to have a little bit longer baselines, because for many applications, especially in the built environment, we would benefit from a bit better height precision and a longer baseline, so loosening the orbital tube would help there for a limited part of the mission. So these three recommendations I would like to bring up for discussion.
Thank you, Ramon. Can we discuss the first one? You said distributing methods rather than data.
Yep.
Could we change that to with the data? Because some may not be, let's say, capable to the methods we're talking about, for example, for ETAD, are all in all are quite complicated. And if everybody wants to implement and test that. And,
I understand the point, but I think if you see the last couple of years and the way that ESA operates, along the mission, there are updates on processing methods, and that's great. And of course, if the whole archive, if there's a little change and we process the whole archive, it would be nice, right? And if it would be available tomorrow, it would also be great. But often, I think programmatically, these are big changes which take a long time. And so I think in making the methods available, that allows for more agility for many users, because they can simply apply the correction themselves. And they do not need to wait for the whole reprocessing of the entire world, for example. And I think ESA cannot accommodate a single case study, so they have to operate on a global scale. And these things are, it's a trade-off. So making the methods available, sharing the code, that's great.
Yes, for example, for the RFI correction, there shouldn't be any issues just to put the code on GitHub somewhere, and then those who want to apply it, they can get it from there. For the radio interference correction, okay, just put the code on GitHub, like some people do, like ICE, for example, from JP. All the software is available, and then you can download it yourself and apply it yourself.
But you have to refocus the data.
Yes, okay.
So this is indeed something that is done at level 0 level, so we need to refocus. But the comment is true. Today we are. I think that with the Sentinels, we are working in an unprecedented time frame. I mean, we have that goes much beyond all of us, and it's clear that we can't rely anymore on the expertise of a single person or a single company. We need to share to make our knowledge open, so that it becomes sustainable beyond ourselves, and that's one of the reasons that we are now entering into a process of fully refurbishing the SAR processor and making it, we hope, open source and available to the user. So we're entering here in a long process again, 2 years, 3 years. It doesn't matter, it sounds long, but if you compare that with the time frame that we have in front of us, it's something that is quite short, and the idea is exactly this one. Reprocessing the data is painful, but if we give you the means of doing that, and the means of doing that for where you actually need it, probably it becomes less painful for all of us.
So for the RFI, I mean, Ramon, you said reversible corrections. Well, for RFI, it's not possible, you know that, because we have to refocus the data, right? So the damage is done. But how about my recommendation for ESA would be support studies. Actually, there are a lot of publications already that they look at the browse images even and detect RFI. Those, because we know, I mean, the study that was shown today showed that probably we don't need to apply RFI all the time, right? So how about a study that ESA supports that come up with an algorithm that run through the archive, detect those which are affected by RFI with whatever the algorithm is, and then at least reproduce those with a version of the RFI correction, then I think that should satisfy what Ramon said also. There will be two versions. The damage is done in one and not the other one, at least, has been tried to correct.
I don't know, I have nothing to comment. That's, but indeed, there is other corrections that are not reversible. RFI, the first one that we have been facing is the denoising, for example. It took us, and we realized that Sentinel-1 has been the first one putting cross-fault data systematically and available, and we have realized over the time that in order to really use this cross-fault data, which have a low signal, we need to denoise the data. And we didn't anticipate that very well at the beginning. It took us a bit of time to get at the point where we are now, which we are pretty satisfied. But this correction is destructive. So we take the decision to not apply it because we are not sure about the correction that we'll be doing. So it was more conservative to not do anything, don't touch, rather than doing something that is destructive and doing something badly. So it would have been worse. You can place the recommendation. We'll have a look to it.
Yeah, but can you give the microphone to the...
No, I mean, those are excellent recommendations then, but I'm just wondering about still the first one, because it's true that maybe we do not provide yet the algorithm or the code, let's say, but this is changing as Nuno expressed. But the methods we typically do. So at the moment, basically all the algorithms for Sentinel-1 are publicly available. All the level 1, level 2 processing and ETAD, everything, it's documented and available. The question that I have is if this information is good enough, if it's written in a way that satisfies the community, or if we need to improve the description of the algorithms that we provide to make them then more useful for everyone.
There is another question. Also there, just to increase the number of comments. Then we go back.
Is that on? Yes. To
Yes, we hear you.
I want to second Ramon's recommendation in the sense that if, I think there's a difference between somebody implementing a paper and somebody running an official release processor. If I run an official release InSAR processor to create either an ETAD correction for a data set that doesn't have it yet, I could actually give it back to InSAR and it could be integrated into the archive. And we could grow an archive as a community instead of always having to rely on InSAR to do it. So we at ASF could implement a version of the processor. People could run the correction on demand. Once we have the correction available, we could give it back to InSAR to add it to the archive. If we implement it ourselves, it's not the same correction. It doesn't have InSAR's level of approval behind it. So I think if one has, similar to what, say, ICE is doing on the US side, is we can build an official processor that processes NISAR data, and InSAR could take it and implement it, and create products that are not just NISAR-like products, but NISAR products that are the same product. And so this way we could add it back to the archive, grow it back into the archive. So Ramon could run the processor, and if we have a way of giving the data back to InSAR, we could grow the past archive that doesn't exist yet without having to rely only on InSAR as a source to do it.
Just a quick addition to this provision of the methods. I think it's good enough already, but can we get also the validation data set? As in,
we can write the implementation then in the same way as ETAD is being implemented, but can we get like the validation data set on which we can verify if our implementation is correct, as in the network of corner reflectors and the expected timing errors that we are about to get?
Yeah. Richard, this there is no answer, no comment. I'm noting that methods and validation, and this brings me to a point that I wanted to bring up. This session was about atmospheric correction, InSAR correction, about interferometry, and so we have seen some numbers, some ways to provide numbers. It's easy to get the absolute position of corner reflector. It's more difficult to quantify the performance gain on an interferogram. We have seen variograms based on Ramon's early work on the atmospheric energy distribution and the correction. That for me it's a nice way to see the improvement. But maybe there are other ways, and if we go forward and we have seen increase of ionospheric correction by 33% or minus 5%, different numbers, different methods. Could we find more, let's say, or recommendations how to quantify corrections on interferograms, on test cases, on data sets, on methods and numbers, how to do that? Are there any more comments on that? Alternative methods or ideas? So for me, the variogram is a straightforward one, but even you always need a reference point. We've seen corrections on volcanoes, maybe a different story. Variogram assumes zero motion, usually.
What I suggest there, or an idea, is to have some intercomparison studies, so where you have a test data set which shows some specific phenomenon, and then everybody can run its ionosphere estimation algorithm on it, and then one can compare.
But what is the truth?
Well, that's the question, of course. So
the majority?
No, but at least it's on the same data set. There's so many studies. You have this test site, and we have accuracy of 95%. Is this now better than the other study with similar numbers? So with the same data set, it provides a better mean for intercomparison.
So I have myself some low-tech recommendations. Well, coming out of the troposphere and ionospheric correction session. Last time I tried tropospheric correction downloading models from ECMWF. It never really worked, so I switched off the tropospheric correction because it's just too much a pain to wait until the data download. I don't really know whether this problem has been solved, but I guess that is something what could be a recommendation to easy to make sure that this is really working well.
Do you want to ask us?
The downloading of corrections. Maybe somebody else can say something about it, whether it's working well or it's not working well.
At least I know for the forecast models, it's a pain, and actually it's a lot. There is a license and all that, but I agree with you. If ESA can push that, make it very clear that it's very important for this community, and we would get it through ESA, that would be nice.
For what? I'm not sure
to make download like it should work. You just download and it comes. But
for the data from ECMWF, you mean?
I'm talking about ECMWF, yeah, and the license thing.
So it's a recommendation to ECMWF. I think that in terms of data download, I think that we don't have had such a problem. When we were working with Antonio in the first years of the ETAD, we used this API that ECMWF has put in place in order to download automatically data from the climate data store. And it was super convenient. You define your layers, the layers that you want, the time frame that you want, and the geographical layer that you want, and you get it. And you get it. So it was, I think, really advanced, and it was working.
It's
really
super
well.
convenient when it works, but when it doesn't, then it doesn't.
Well, yeah.
Then we can control the distribution because the layer being
Because I've done our base on Airfile data.
yeah, we are downloading the data from the CMWF and we encapsulate it in the product. So in this sense, it's a way to overcome this.
I think for us it's clear that there is no way we can push ECMWF to make I think to make them evolve in their data access. It has to go through ECMWF. We have a specific agreement with them. We get the data with them in a certain way, not only for Sentinel-1, for all the Sentinel, for all the explorers. That's why we don't have that pain. They are actually putting in place a specific service for us, so that's why we don't suffer that much of a problem. But as Muriel mentioned, the data will be in the ETAD layer, so you can get it from there.
And so maybe that was your question, the way you meant the question, but I think it's maybe less important to evaluate the performance of these methods on sort of a global scale, because I think that's maybe reasonably meaningless, because it varies dramatically based on the local topography and based on your site. But my feeling is that the number of people that will be working with InSAR data is going to continuously grow, and many of them do not know too much about the error sources. And giving the user something, as a list of recommendations, is like, here you have layers that you can use to correct your atmospheric effect. Here's some methods how you can evaluate whether that layer is useful for you. It's like, calculate a variogram, look at the variogram. So to give, we'll be providing these layers with the product, and in some places they will work great. In other places they may not work so great. The ECMWF layer will work much better if there's topography. If there's no topography, it may not do much to your atmospheric delay. And having some recommendations for the user to evaluate whether the layer is useful for their application could be quite helpful for many users, I think.
Giovanni, do you want to?
Yeah.
I think it's on.
Yeah, is it okay? Refer to what our colleague suggests to have some common data set where all the community can train the methodologies that have been developed. Maybe one possibility to have something that Ricardo did in the past, some kind of supersites for atmosphere, in the meaning that the method should correct, but besides this also explain. Similar approach to the methodologies that AI algorithms that are applied, but now people is working on explainable AI, so it can be some kind of something that can be explained physically. So we can select some sites which are prone to important atmospheric artifacts, where to add other in situ data besides AeroFi, which is just one of the data. The community can contribute with other data. And then, I don't know, the different methodologies can be in competition to correct, but also to explain, because there is no truth, actually. It is almost, there are some comments about this possibility.
There might be some sites with some truth, some atmospheric sounders, GNSS, of course.
I have a question. Yes, okay. I have a question. Before on NVSAT there was Maris.
No, we don't hear
There was Meris on NVSat before that took images, multispectral images, at the same time as the radar. And we could have the precipitable water vapor integrated. And it was quite, sometimes without clouds, the correction of tropospheric effects was not so bad. And for the validation, is it possible to have some multispectral images at the same time, or almost the same time, as SAR images, to validate the algorithms?
Something like that, but really within 15 minutes. No?
Yes, maybe. Is there a satellite which is close to Sentinel, a multispectral?
Following the SAR.
Chi maybe is the closest. I think in Sentinel-3, but Sentinel-3 there is the radar altimeter, but there is also the multispectral instruments like Meris. But I'm not sure if there is where there are crossovers with Sentinel-1, for example, because they are not in the same orbital plane. They have different altitudes. So the good thing of Meris is that it was flying in the same platform at SAR, and you can have the two together. Now it's not possible.
I think we have earned at least one beer until now.
I have just one question to the audience. We have seen from the presentation of Heresh and the presentation of David, how and also from the presentation of Ricardo, how efficient to have our SSC data in a common grid. Co-registered grid or geocoded SLC. So is there a consensus in the community towards what we should do for our future SLC products? Should we make such that they lie in a grid? Which grid? Are we all happy about it? Or is there further work that needs to be done in order to make sure that we are taking here the right decision? I think that with NISAR, you will be the one, the first one going to that direction. So we'll learn a lot from you. But is there any consensus on what we should do for Sentinel-1, but also Roselle or NextGen?
Obviously, we are going to the geocoded domain to align everything. So, and I think for Sentinel-1 is easier than NISAR because it's C-band. So.
Yeah, so I said, we don't want to ask to you. We know the. So the question was clear. So do you think it's better to stay with this conventional approach, or it's better to move to something different in terms of identifying a reference grid to be selected, let's say, in an appropriate way?
I think it's premature to ask the question, what's the CSLCs are produced by Opera, then people will be able to play with them.
Yes, and I think both NISAR and Opera deferred this decision, right? Because we have both. There will be the traditional SOCs and the geocoded ones, and you could let the community vote and see who's picking what.
In NISAR is having that. With Rosette, we'll also see that. At some point, maybe we have to move away from the paradigm of processing all the data systematically. With Rosette, we have the data multiplied by a factor of 10 downlinked with respect to Sentinel-1. The SLC will be multiplied by a factor of 5 with respect to what you have. So it's a dream to think that we'll have both of them for Roselle or in the future. So we need to make a decision, we need to have a clear guideline from you, or we take no decision, and then, as Ramon was proposing, why probably the good solution is not to choose, but to provide the tools for the community to do it by themselves. Could be.
Okay. I have concern regarding these geocoded SLCs, especially for the applications in built environments and point-scatter geolocalizations. When we do geocoded SLCs, when we have geocoded SLCs, then the precision and accuracy of that geocoding is very dependent on the topography and DEM that we already used. So for tectonic subsidence, maybe it doesn't matter, already accuracy is good, but when we go to the cities and really we want very precise geolocalizations on the building and infrastructures, then if we have already geocoded SLCs, it's very difficult to reverse that to original SLCs and then again process more precise geolocalization for built environments. So for those kind of applications, having SLCs not geocoded is much better because they need precise height and topography, and this is different case to case, and people usually do it in the post-processing to have very precise geolocalizations. But if we have already geocoded, then just purely geocoded SLCs, then we cannot improve geolocalization based on that. Again, we need raw SLCs with all the orbit information to do precise geolocalization. This is the drawback that I see in the geocoded SLCs, at least for those kind of applications. Thanks.
So thank you. I think we take Paul's recommendation and put this auf Wiedervorlage, as we say in Germany, which means we don't decide today, but maybe at next Fringe, put the question again. Do we have any other pressing question which may reduce the number of years?
Very last question.
Thank you. Yes, I was just going to go one step further than Sammy's excellent comment and point out that whatever we do with the DEMs also needs to work for places where the topography is changing rapidly. And that's using a static DEM for those co-registration products will start causing lots of problems for applications too.
Okay, that's really the last one.
So I think regarding the comments about the geocoded SLC, yes, of course, there would be, as I showed, there could be geolocation errors due to the height errors, but your life will be similar in the radar coordinates too. You have to take at them, do some geometry computations, and resample to the grid of your choice, which could be, a radar grid. But you have the same errors. So your at the end, your geolocation is off because you need it there. So yeah, the geolocation is off. You can do actually time series and estimate the DEM errors and all that. No reason why you couldn't do that. About the change of the DEM, that's, yes, of course, that's a good comment and a concern. If it happens, yes, things needs to be resampled to some better grid that represents it. But again, your life is the same in the radar coordinates too. You have to do it. You had a good comment. They didn't hear it. How about the split spectrum? Yes, that's the main drawback of the geocoded SLC. We cannot split the spectrum anymore. We have lost the range Doppler. And the only solution right now that I have is to split it and geocode the sidebands as well.
One can see it's not only split bandwidth, it's everything you want to do in range and azimuth. So if you keep a natural acquisition geometry, this is what you want to do. If you want to filter anything in your face. But once you have filtered the face, then you can geocode. That's fine.
Yeah. But we postponed that already.
Yeah, postpone it. But you can start. Yeah.
Okay. So, thank you all. It took some